New chapter, and this is called the thermochemistry. So chapter 6, thermochemistry. So what do you suppose we're going to be talking about in this chapter?
Temperature.
Yeah, and something else related to temperature. That causes temperature changes.
Like energy?
Okay, in the form of
Heat?
heat. Okay, right, so energy in the form of heat. So first of all, energy. Let's talk about what energy is. What is energy? Jacob?
Ability to do work.
Yep. So we'll say it's the ability to do work. The ability to do work, but I'm going to add something else in there. To do work or produce heat. By the way, just as a side note here, we're starting to get, teachers starting to get the automatic polls of what class you should be going into next year. Okay, and I pretty much reviewed everything, and most of you guys are pretty good. Just a couple notes. If you were an 85 to 87, I went and changed the recommendation and said you should stay in honors. Okay, for some of you guys, that's in particular for juniors. Okay, because the automatic poll I think is 88. Okay, I think if you're getting 85, 86, 87 in here, you're going to be fine in physics honors, and I think Mr. Bible's cool with that too. If otherwise, you're going to be put into, you know how that works. You know, if you get a 93 or above, you go up. If you're at the B level, you're going to stay. If you're at C level, you drop. If there are any things that you need changed at the end of the year because your grade has changed, you need to come to me and talk to me. I kind of told a lot of you that already. The other thing is, something I saw was goofy, was particular for 10th graders. Okay, so you 10th graders, you guys got other options, right? There's other things that can happen. So for instance, just as a note of example, because things are changing a little, I noticed that they took Carson and they automatically put you into a physics course, where really you should have your choice next year, is my understanding. And the rest of the 10th graders, they either put you into AP Environmental or Honors Environmental, where in reality you should have a choice of maybe Bio AP or Chem AP or some other choices, okay? So I don't have the answers to those things yet, but the point being is this: if you're going to be a senior next year, you're going to be taking some level of physics, okay? If you're going to be a junior next year, you have some options, is my point. And the options, some of it will be limited based on your grade, but when we get to selecting classes, you can talk to me if you need to, okay? All right, so just a side note there. Okay. So energy, okay, so that's the ability to do work or create heat. And we know that in the universe, energy must be conserved. What does that mean? Go ahead, Drace.
Energy can't be created or destroyed.
Yep. Law of the conservation of energy. Okay, so we know that energy is neither created nor destroyed. Energy is neither created nor destroyed. It is only transformed. Now, if you really want to get trippy here, we kind of think sometimes as energy and mass as being separate things, where in reality they're one and the same. Okay? When you measure mass, you are measuring energy, actually. You know, equals mc squared? Okay. Energy is related to mass times the speed of light squared, okay? So in reality, like let's say you take a battery and you run it dead, that battery actually weighs less than it did when it was full because it lost energy. It's a very small amount, okay? But it's a measurable amount, right? So without getting too crazy, we're just going to keep it simple and say this. The amount of energy in the universe is always the same. The thing is, though, is the universe is getting bigger and bigger. So what's happening to the energy? It's becoming
thinner and stretching out.
Yeah, more stretched out and dilute. Yeah, and that's kind of the nature of the universe. Okay. Now, there's two main types of energy we talk about. What are the two main types?
Kinetic and potential.
Kinetic and potential, and I know a lot of you guys know that. Potential energy versus kinetic energy. Okay, so I'm going to ask you the one that you're going to get right. What is kinetic energy? Matt?
It's like the energy that a object is exerting when it's moving.
Yep. Energy due to motion. And so you got to be careful with kinetic energy because, as Einstein said, things are relative. So right now, I'm relatively motionless to you guys. I mean, I'm not really coming at you or going away from you, right? But relative to the sun, relative to the moon, relative to the galaxy, I've got a lot of kinetic energy. The Earth's spinning, the Earth's going around the sun's going around the Milky Way. So relative to those other things, I have a lot of kinetic energy. But relative to you and me, I don't have none. Make sense? Depends on what point of view you take. Okay. Now I'm going to ask you about the one you're probably going to get wrong. What's potential energy? Don't be afraid. I got the same two guys answering everything. It's potential energy. What do you want to say potential energy is?
Can I use like an example?
Nope. I want to know what it is. Ronnie?
Energy like built up before the release.
Okay, so that's like, no offense, but it's like kind of kindergarten-y. Nobody else wants to take a stab? What do you think, Matt?
It's the measure of the energy that can be exerted by an object.
Energy due to position.
Hey! Did we talk about that this
Less, more. I just remember it
Perfect.
from like 7.
year? It's energy due to position in a system. So try and make sure you learn that definition because that is a much better definition of potential energy. Energy due to position in the system. So think about it. One of the types of energy that you guys know about is what? Gravitational potential energy? Got a rock on a cliff? Well, why? Because it's on a cliff. What's the system? It's high up in the air. It can potentially fall down low, right? But potential energy could also be like the energy in a bomb. Well, what's the position in the system have to do with that? In a bomb. What are the things in the system that their positions matter?
Going off.
What's that?
Being able to go off.
Yeah, but why?
From impact.
Okay.
The fuse and the gunpowder or whatever.
Okay,
the
we're getting
fuel
closer.
is are very like close together. They're positioned in.
Okay, we're getting
manner.
closer. It's the structure of the molecules that make up the explosive. The positions of the atoms in that molecule. That's what makes it explosive. You follow that? Okay. All right, so position energy due to a system. Okay. Okay, now next. What's heat?
I think it's the measure of the average kinetic energy of the particles.
Well, that's temperature. What's heat? Use that word all the time. Jacob?
Is it the amount of energy it takes to talk about something?
So that's not bad. That's not bad stuff. Ronnie, another try?
Product of energy.
Okay. All right, go ahead.
The amount of energy a system gives off.
Yeah, actually, that's even better. It's the transfer of energy between two objects. So, like my big fat white cat keeps jumping up on my wife because she's off all this couple weeks here. And so, you know, she lays on a couch or something. The cat jumps up on her and she can feel the heat, the transfer between the two objects, right? You have a heater in your house or a furnace, right? So the transfer of energy is between the heater and the room. Okay, so, all right. So again, these are all terms we're getting out because they're going to become important here shortly. What do you call work? Physical, in terms of physics. We got 3 guys in this class? 4, Ethan.
The energy exerted to do something.
Close? Okay, when you say do something, that's the part that I'm tough with. But the energy exerted to what?
Energy inputted,
To do what?
Perform a task.
Close? I mean, I want to be a little more specific than perform a task.
Go in motion.
Yeah, to what?
Go in motion.
Okay, all right. So it's a force applied over a distance. A force applied over a distance. So, you know, if you just like sit there and push on an object, push on an object, push on an object, and it doesn't move at all, have you done any work? No. If an object is in motion and you're not applying any force to it, is any work being done? No. The force has to be applied over a distance. So, like when, let's say a skydiver jumps out of a plane and is falling, that actually is work because the force that's being applied is gravity. There is a force, okay? But now let's say you're in deep, dark outer space and you shoot a bullet, that bullet's going to keep going and going and going and going and going if there's no forces acting upon it. That's not work anymore. The work was initially done when you shot it. But once it's on a cruise and nothing else is affecting it, well, there's no more work being done because it has to be a force being applied.
Could you shoot a bullet in space since there's no oxygen to ignite?
You'd have to modify it so it'd have oxygen to burn, yeah. I mean, I'm sure they could do that, you know.
So if you did shoot a bullet in space, would it just continue at the same speed?
It would pretty much stay at the same speed, yeah, until some other force affected it.
So it could be dangerous for millions of miles?
Yes. Yeah,
So
absolutely.
drop it off.
But then stop and think about this, though. A bullet goes, how fast, hunters, guys, how fast do they go? Several hundred feet, up to 1,000 feet per second or something like that?
766.
766.
So,
Yeah, I figure that's a nice round number, right? So that's moving pretty fast. The micrometeors that are on the size of a bullet that hit the Earth every day are going way faster, way faster. They're going like some of them are going 60,000 miles an hour, 45,000 miles an hour, which is a lot faster than the maybe I'd have to do the math, but 700 per second. You're probably going in the hundreds to thousands of miles an hour. I would think. I could do the math, but I don't know it off the top of my head.
So since there's no gravity in space,
Well, there is, but it's not much. So let's
okay,
just be clear on
so
that.
Since there's so little
Yeah.
gravity in space, what determines which way does it pull when the star falls out of the sky?
It's not. First of all, it's not a star falling out of the sky. All right. What it is it's the remnants from comet tails. So as comets go around the sun, they leave debris behind them, and that's us flying through their path where they had been at one point. Okay. And so what those are little pieces from grains of sand up the size of pebbles and little rocks. What determines what direction they fall? Well, it's more a matter of what direction the Earth plows into that trail. So you have this trail of dust and the Earth coming through and it's plowing through it.
So how do we determine which way is like up and down in space?
So how you define it.
So it's just what perspective you're at?
Yes, it's a matter of perspective. There's no reason why we had to say the North Pole was up. Basically, the reason the North Pole is up because us Western people most of us are Western European kind of people. Well, we lived on that side of the globe, so we wanted to call that up. You know, it's pretty much a human thing.
So like there's no like blood rush at any time in space, it's just your blood's even throughout your body.
Well, it does rush to your head because usually you're used to it being down lower, right? So when it redistributes, it feels as though it's rushing to your head. Yeah. Cool. Okay. So now we get into some real terms here. A state function or state property. Okay, so now we got to get into some funky terminology here. Right now, you're sitting here, probably reasonably comfortable in terms of temperature. Okay, reasonably comfortable in here. Does the fact that you're reasonably comfortable right now depend on the fact that you had to come to school in the cold this morning?
Yes.
Not really. What if you came to school today and it was hot out before you got here, but you're at the same temperature again? Does it matter what went before? No, it doesn't. Okay. My pop is cold right now. My pop's cold because I just took it out of the refrigerator, right? Does it matter that this sat in my garage basement for a while, or garage floor for a while, or sat on a shelf at Wegmans at room temperature, or sat in a warehouse, or sat on a truck? Do any of those things matter in the fact that it's cold right now? No. Okay. Does what I weigh right now depend on what went before? Yeah. It depends on what my diet's been over the recent long term, right? Recent short to long term. So the point is that some things you can look at and say, it only matters because of the here and now. The here and now is all that matters. Or some things I can say, the here and now is only the way that it is here and now because of what went before. Okay? So like, certain things had to happen to lead up to a certain state. Okay? Or, it doesn't really matter what happened before, it's only about what's going on right now. A state function's about the here and now. Okay? It's a characteristic. That only depends upon the here and now. Only it depends upon the here and now. So the pathway to the current conditions does not matter. Okay, so for example, let's say current temperature, is it stopping?
Oh, it's catching up.
Diet.
Is for
Okay, now pathway. Pathway is the specific steps involved. Involved in a process. So maybe Mountain Dew from the factory to me. You know, how the Mountain Dew got from the factory to me, that is a specific pathway. So it was made, and maybe it's thrown on a pallet, and maybe it's thrown on a truck, and got sent to a warehouse, and maybe on another truck to another warehouse, eventually to Wegmans, or somebody brought it out from the back and put it on the shelves and in my cart, and in my truck, and into my house, and into my floor of my basement, or my garage, and then into my refrigerator, and then into my book bag, and then in my truck back. All those little things are the pathway, right? Now, think about it like this. Here's another simple way to think of this idea. You remember at the beginning of every year, we go up to PVAC for a mass. Okay? Now, we walk a specific route. We walk down 10th to Cherry and then up Cherry. But couldn't you go some other routes? Right? You could go some other routes that are equally as efficient. Maybe you go up to 11th, across 11th, up Cherry, right? Or maybe you go up 11th, or up Myrtle here to 12th, and then you cut across the Cherry, then you cross there. lots of different direct paths, but there's no reason that says I couldn't also too drive or walk out to Harbor Creek, then walk across the bayfront, and then come up the bayfront and then go there. Even though it's not a direct path, it's a path. Right? There's an infinite number of paths I could get from here to there, basically. You with me on that? So the pathway would be the specific way that you got there. But once you're there, if you started here and you started there, how far are you displaced from where you started? The same, regardless of any path. How far I am from my starting point. If you're here, and now you're at PVEC, doesn't matter how you got to PVEC, you're that far away. So that distance you are from your starting point is a state function. It doesn't matter the path that you took. Now, how long it took you to get there doesn't depend on your path, right? So the time to get there would be something that's not a state function, because that's dependent upon the pathway. Is this making sense? Some things depend on now, some things don't. Okay. All right, now a system, these are all terms that we're going to be using pretty extensively this chapter, is just basically a part of the universe that you choose to study. Part of the universe chosen for study. So it could be a lot of different things. What do you think a system could be for a chemist? Right, what?
Periodic table.
Nope. Come on, I only got 3 guys in this room now? Nobody else knows anything? You guys are honor students. What would be a system that a chemist would study? All should have an answer of some sort, I would think.
Energy.
Okay.
His lab procedure.
Okay, so now we're talking about a lab procedure. How about, say, the contents of a beaker? Maybe you put some things in a beaker and you study. What do you think a system could be if you're somebody who studies climate change?
Africa.
Okay, so Africa, I'm going to say, how about the atmosphere? Earth's atmosphere? What if you're somebody who studies, I don't know, stellar evolution? Evolution of stars.
You study like the sun.
Okay, the sun. Yep, you can study the sun. How about the Milky Way even? Because we can see stars throughout the Milky Way. All right. So, but the point is this. You as a scientist define the system. Okay? Now, the system is anything that's in that defined area. So, in the context of a beaker, it might be all the chemicals that are in the beaker. It might be the temperature inside the beaker. It might be the colors that you see inside the beaker. But everything outside of that beaker, we call surroundings. So this is everything outside of the defined system. Everything outside, bless you, of the defined system. So basically, if you're talking about the contents of a beaker as being your system, everything else in the universe is surroundings. And if you're talking about Earth's atmosphere, everything besides Earth's atmosphere is surroundings. You're talking about the Milky Way, everything outside our galaxy is surroundings.
So if we were like talking about the Earth's atmosphere, would like the land and the crust of the Earth be surroundings? Or?
Depends on how you want to define atmosphere. Typically, atmosphere is the gaseous part. But now, if you want to say, I want to study the Earth's atmosphere, lithosphere, and what's water? Bathysphere? No. What is it? Hydrosphere. Talosphere. Is it? I couldn't remember. It's been a while. Okay, now, so here's where a lot of this stuff becomes an issue, is we're going to be talking about energy and the way energy flows. okay? So like in a beaker could absorb some energy or it could release some energy, right? Hey, what's up? Which ones do you have to do yet? Okay, good. Because I had to get a water bath for the other one. So, endothermic. What's endothermic mean? You guys should know this. The same guy answered every time. Endothermic.
In energy?
Yeah, energy goes into the system. Or energy flows into the system. Now, I'll tell you this when we take notes in the future here, starting on Monday or Tuesday. Chemists always take the point of view of the system. So if energy is flowing in, we're going to call that positive. Follow me? Positive energy. Troposphere. There you go. Well, that's part of the Earth's atmosphere, the air atmosphere. Troposphere. I'm trying to come up. What's the oceans? You don't have to look it up. Don't worry about it. Exothermic. Energy is going to do what? Yep. Energy flows out of the system. And so we're going to call that negative values. But here's where we got to be careful. I mean, there's no such thing as negative energy. You either have it or you don't. Thanks, sir. But we're just going to use signs to indicate direction. Robert Harris. Robert Harris. For later today. Do you know about it? Okay. Okay, but we'll get to that later. Last two terms. Thermodynamics. And so thermo obviously has to do with what? Heat, okay. So, and then what's it mean to be dynamic? I'll tell you this. I've always been a fan of very dynamic music, and I mean this seriously. And that's music where there are quiet parts and there are loud parts. It's not all just loud, it's not all just quiet, but there's parts where there's crescendos and builds and drops and stuff like that. So what's it mean to be dynamic? Changing, yeah. So this is the study of energy and its conversions, the way it's changed. The study of energy and its conversions, which we'll be looking into. And lastly, first law of thermodynamics. There's several laws of thermodynamics. You can learn about them in physics. And we already said this is basically the law of the conservation of energy. Basically, the amount of energy in the universe is constant. And that's all I got for you today. Cool. So just a bunch of terms, and then those terms are going to become important going forward.